Hello there. In this video we're going to work through a few examples on how to determine whether a word problem is associated to a geometric, binomial, Poisson, or hypergeometric random variable. And we're also going to work through how to actually solve those particular probability problems. Alright, so let's look at our first example. Let us assume that research studies have shown that the likelihood of randomly selecting an online retailer and it being fraudulent is approximately 9%. And let's assume you place 15 retail orders independent of one another across a given month at different retailers. What is the likelihood that less than 5 of those orders of 15 are actually fraudulent? So just a couple things to mention here. So the number, so we're going to let x be the number of fraudulent orders in your set of 15 online orders, because we need to sort of define what x is. So if this is the case, clearly x is a discrete random variable. The values of x can range from 0, 1, 2, 3, 4, up to n, where in this case n is equal to 15. So either none are fraudulent or all 15 of them are going to be fraudulent. And we're also going to assume that each event or fraudulent order is independent of another. So if we know these things, and let's assume the probability that this order is fraudulent is known, in this case it's given to be 0.09. So if we have all 4 of these components, then we can say that x is a binomial random variable with probability of sex p is equal to 0.09 and parameter n is equal to 15. And we want to know the probability that x is, so we want the probability that less than 5 orders are fraudulent. So the probability that x is less than 5 is going to start at 0, so the probability that x is equal to 0 plus the probability that x is equal to 1 plus x equals 2 plus x equals 3 plus x equals 4. So let's focus on this term briefly. So what is the probability that 0 orders in your 15 are fraudulent? So that's going to be equal to 15 choose 0, so 1 minus the probability of fraudulency, so that's going to be 1 minus 0.09. So if that is the case, then what do we have? So if 0 are fraudulent and the probability of fraudulency is 0.09, this is the probability of not being fraudulent. And since we're interested in 0, that's going to give us, of course, 15 different non-fraudulent orders. And we're going to have 0.09 raised to the power 0 because we have 0 fraudulent orders. And then we're going to add to that the probability that x equals 1, so that's going to be c 15 choose 1. 1 minus 0.09. So now we're going to have 15 minus 1 non-fraudulent orders, so 14 good ones, and 1 fraudulent order there. And we're going to continue all the way down to this last one, which is going to be 15 choose 4 times 1 minus 0.09 to the 15 minus 4 times 0.09 raised to the power of 4. So we can write that in a more compressed way. So the probability that x is less than 5 is going to be equal to the sum from x is equal to 0 to 4 of px. So it's going to be equal to the sum from x is equal to 0 to 4 of 15 choose x, since that's the term that we are varying across. Also, we have 1 minus 0.09 to the 15 minus x times 0.09 raised to the x. So either you can do all 1, 2, 3, 4, 5 of these terms manually, or you can have a calculator or software to do this approximately for you. So if you find this out, then you're going to find that the probability that x is less than 5 is approximately equal to 0.9918. So there's a 99% chance that this is going to occur. So remember that the expected value of a binomial random variable is going to be equal to n times p. In this case, that's going to be 15 times 0.09, which is equal to 1.35. So out of our 15 orders, we're expected to get anywhere between 1 and 2 orders of them being fraudulent. So the probability that you get 5 or less is going to be extremely likely in general, which is why this number is so high. So let's move on to the next example. Alright, so for our second example, let us assume for a large company, it has recorded that, so that should be that, its complaint department receives on average 1.2 calls every minute. If the calls are uniformly distributed across every hour from 4 o'clock and 10 o'clock p.m. Eastern Standard Time, if each call is independent from one another, what is the probability that you receive more than 50 calls between 9 and 10 p.m.? So let's just write down a couple things before we start identifying how to solve the problem directly. So we're going to begin by letting x represent the number of calls received between 9 o'clock and 10 o'clock p.m. Eastern Standard Time for this particular company. So what properties does x represent? So x can take values 0, 1, 2, 3, 4, because you know people can call, it's possible between these couple hours. 5, 6, you could technically have 1 million unless you have a cap on this, and this is going to go up to positive infinity in theory. So this is a discrete random variable, so x is a discrete random variable. So it's a discrete random variable which is bounded below by 0 and is not bounded above. Each event is independent, and the average number of occurrences in the interval 9 to 10 p.m. is quote-unquote known. Now, it's not directly given to us between 9 and 10 p.m., but we're going to discuss that in just a moment. So if all 4 things are given, that means x is a Poisson random variable. So x is a Poisson random variable with parameter lambda. So lambda is going to be the average number of successes or occurrences of phone calls between 9 and 10 p.m. So let's pretty much get that value out. So it says that on average 1.2 calls every minute. And it also says that these calls are uniformly distributed from 4 o'clock p.m. to 10 o'clock p.m. So these calls are pretty much uniformly distributed. So we can partition this block up into the particular region for which we want. So if we have 1.2 calls every minute, that means we have 1.2 times 60 calls on average every hour, which means we have 1.2 times 120 calls every 2 hours. And we only know this if the distribution of the calls is uniformly distributed over a particular block of time. So that means lambda is going to be equal to 1.2 times 60 times 2, so 60 minutes per hour, 2-hour block for which we're interested in, since we're focusing on 9 p.m. Is it 9 p.m.? Okay, so let's just do, let's just do 9 p.m. So that's going to be 1 hour actually. Alright, you know what, let's just change the problem a little bit completely. Let's do 8 o'clock to 10 o'clock p.m. Let's focus on this problem instead. It's a little bit more interesting. All right, so that means that lambda is going to be equal to 120 times 1.2, which is going to be 144 cos on average in any 2-hour block of time. All right, so we're interested in, so what are we interested in? The probability, so we're changing that to 8. So 8. So we receive more than 50 cos in this block of time. So we're interested in the probability that x is larger than 50. So this is going to be p of 51 plus phi of 52 plus p of 53. Now, since a Poisson random variable is not bounded above, technically we can go up to 1,000,000 and still not have the possible results. So every time we have something like that, we have to go about this in the complementary perspective. So the probability that x is bigger than 50 is going to be equal to 1 minus the probability that x is less than or equal to 50. So this is going to be equal to 1 minus the probability of 0 plus the probability of 1 plus the probability of 2 all the way up to the probability that x is equal to 50. So if we pick any one of these, if this number is small, you might want to do this by hand. So this is going to be equal to e to the minus lambda times lambda to the x over x factorial. So this is going to be equal to what? So lambda was 144, so this is going to be e to the minus 144 times 144 to the power of 2 divided by 2 factorial. And we're going to do this for every single term in this sum. So we can compress that as a nice summation. So the probability that x is greater than 50 is going to be equal to 1 minus. So now we're going to have the sum from x is equal to 0 to 50 of e to the minus 144 times 144 to the power of x divided by x factorial. Just a side note though, e to the minus 144 is a constant, so technically you can factor that out of the sum. So you have the probability that x is bigger than 50 is going to be equal to 1 minus e to the minus 144 times the sum from x is equal to 0 to 50 of 144 to the power of x over x factorial. So once you do out this expression, you'll get that's approximately equal to 1 minus 1.2 times 10 to the power of negative 19, which in general is a really small number, so we can say it's approximately equal to 0. So this is approximately equal to 1. Now make sure if you have any things like this, do not say that this is equal to 1 because that means it's guaranteed to happen. So it's not exactly equal to 1, but approximately equal to 1. So it's really important to denote that difference. All right, so for our next example, let's assume we have a machine that's tested once every hour for quality assurance. Let's assume that if the machine is flawless, then it will pass this test, and if it is not flawless, then it will fail that test. This quality assurance, of course, is not 100% effective in terms of determining whether it is flawless or not. So let's assume previous companies report that on average the quality assurance tests about 60% of the time that it actually does catch a flaw in the system. So if the system does happen to have a flaw, what is the probability that it will be detected within the first 5 hours, so 5 hours or less? So let's list down the possible scenarios. So we're going to define x to be equal to the number of attempts or trials until the flaw, because we're assuming that it does have one, is detected. So x is the number of attempts until the flaw is detected. So the minimum value that x could have is 1, because you have to have at least one trial in order to detect something. 2, 3, 4, 5, and technically it could go out to like 10,000 trials until it actually is effective. So this is technically not bounded above, but bounded below by 1. So we want to know detected within the first 5 hours. So you could detect it on the first trial. You could fail to detect and detect on the second trial. You could fail, and detect on the third. Fail, and detect on the fourth. And fail, and detect on the fifth. So if we assume that these trials are independent of one another, then we can classify x as a geometric random variable. Alright, so remember the PMF for geometric, so that's going to be 1 minus p to the x minus 1 times p. And we're interested in finding the probability that x is less than or equal to 5. So this is what we're going for. Alright, so we know that the probability that x is less than or equal to 5 is going to be the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. So if we want to find any one of these in particular, so the probability of 3, so that's going to be 2 failures, 1 success. So that's going to be 1 minus p to the 3 minus 1 times p. Now in this case, the probability of, let's see, 60% of the time. So it fails its quality assurance test about 60% of the time. So it does not have a success 40% of the time. So failure, so the probability of failure in this case is 0.6. That means the probability of success is going to be 0.4, which is what the geometric distribution is usually phrased into. So that means this is going to be equal to 1 minus 0.4 to the power of 3 minus 1 times 0.4. So the probability that x is going to be less than or equal to 5, as we know, is going to be the sum from x is equal to 1 to 5 of 1 minus 0.4 to the x minus 1 times 0.4, as x ranges from 1 to 5. So once we do that process out, we should get approximately 0.9222, or about 92% chance of this occurring. So let's do another example. So let's assume that you are in charge of scheduling technicians to work on particular types of vehicles for some servicing company. Let's assume that for a particular Saturday there are 28 scheduled vehicles. 5 of them needs their brakes changed, 7 needs their transmission flushed, 3 of them need both a brake change and a transmission flush, and the remaining 15 need a general service. So each of the technicians get assigned 4 cars at random. What is the probability that technician A gets 3 cars that only need a general service and 1 car that needs both a transmission flush and a brake change? Let's see. Firstly, let's just look into the question statement just to make sure everything is in order. So 5 of them need to have their brakes changed. So let's show a little Venn diagram to sort of see what's going on. So 5 of them are going to be located in this circle. 7 needs their transmission flush, so there's 7 of them. 3 of them needs both, so 3 is going to be in this little middle region. So if 3 are in the middle region, 5 are in the blue circle, that means only 2 are here. And if 7 is in the green circle and 3 is in the yellow, that means only 4 are here. So 4, 5, 6, 7, 8, 9 people are in the union of blue and green. So 4, 5, 6, 7, 8, 9. So 9 people are there. And everyone else, so 15, is going to be outside in this region. So we have 15 plus 9, so that's going to be a total of 24. So we need to change that to 24. Bad problem. Always check these in books and stuff just to make sure that everything is well posed. Alright, so let's get a feel for what's going on here. So E is the event that you have a sample that is similar to the structure. So we get 3 cars that only need a general service and 1 car that needs a transmission flush and a brake change. So we have a general service, general service, general service, and a brake transmission flush. So this could be 1, 2, 3, and this could be 1. So structures of this style. Now, since we're gathering a sample, these are going to be dependent samples, and you can't gather more general services than are possible, of course. So how many different types of samples are there in this set? So the size of this sample space, which is going to be the set of all samples of size 4, selected from, we have 24, is going to be 24 choose 4, because we don't necessarily care about the order, we only care about the structures within them. All right, so since we're pretty much pulling particular values out of a sample space and we have a particular number of values for which G can be, so we know G is selected out of 15 people, and this BT values are selected out of 3 people. So it's almost like a geometric distribution. So if we're interested in the probability of getting exactly 3 people inside of our sample that is only a general service, that would be a hypergeometric distribution. But this is slightly different because now we are mandating a particular scenario for the complement of that. So it's actually going to be a restriction of a hypergeometric distribution. So the probability of this event occurring is going to be equal to, so we have C24,4 on the bottom. So there's 15, choose 3 different ways of doing that. Now, if this was a strictly hypergeometric distribution, this next term here, which I'm going to highlight in green, so if we're only focused on 3 general services in this sample, then this is going to be equal to C24 minus 15 and C4 minus 3. So that's how many values in the sample are not general service. So that would come out to C, what would that be, 9, C, so 9, choose 1. But we only are focusing on a particular type of subset or a particular subset of the complement of my general service areas. So there's only one way to choose that, so that's going to be C3, choose 1. So this is going to be my particular probability for which I'm going to be interested in. So once you do all this math out, we find that the probability of this event occurring is going to be approximately equal to 0.128, so about 13% chance of occurring. So of course, if you're interested in the probability of getting at most 3 general services, then you would do 3, 2, 1, and 0, and all possible combination structures of that form. So this is a special case of the hypergeometric distribution, and we've gone through a particular example of both binomial, Poisson, geometric, and hypergeometric. One of the most important things you need to know when you're doing examples like this is to be able to identify what type of random variable you are given. Usually we start determining whether it's discrete or continuous, whether it's bounded at all, and also what parameters and pieces of information we are given. Hope you enjoyed.